Hey everyone, I hope you're doing well today. In this video, I'm going to be just going through practice problems of finding rational zeros of cubic and quartic functions. Here's the first function. Looking at the highest degree, right away we know that this is a cubic function. Since it's cubic, we know it's going to be an odd function. Also, our leading coefficient is positive 1. Based on that information, we know that our graph could look something like this. As x approaches negative infinity, f of x is going to be approaching negative infinity as well, and as x is approaching positive infinity, f of x is also approaching positive infinity. While there may not always be a rational zero, all the examples in this video will have at least one. To find our list of possible rational zeros, remember that we need to find what our p-value and q-value are. The list of possible rational zeros of this function are going to come from the ratio of the factors of p over the factors of q. In this function, p is negative 24 and q is positive 1. Here are the factors of p. And here are the factors of q. Listing out all the unique ratios, we have: if there are going to be any rational zeros for this cubic function, it has to be on this list. To find out which one of these is actually a rational zero, we're going to have to either use polynomial long division or synthetic division. Since I find synthetic division to be a little bit quicker, I'm going to use that. Since it's a cubic function, we just have to test out values until we find one that works. The reason why we only have to find one is because then we'll have a quadratic factor, and we can either factor that, complete the square, or use the quadratic formula to find the other zeros. I'm going to start with negative 1, so I'll put that over here to the left. Then I'm going to write the coefficients down of 1, negative 12, and 35, and I write the constant of negative 24. For synthetic division, I'm just going to bring this 1 down here. 1 times negative 1 is going to be negative 1. Adding these will get negative 13. Negative 1 times negative 13 is positive 13. Adding 35 and 13, that'll be 48. And negative 1 times 48 is negative 48. And we know that this is not going to be 0. Remember, this value here tells us our remainder, and if it's not 0, that means it's not a factor. Now I'm going to try positive 1 here. This is good news for us. Well, yes, there are 16 possible ones that we could have tested. We were lucky enough to find one of them on our second try. Since 1 is a 0, that's the x-intercept, so we know that x minus 1 is going to be the binomial factor. X minus 1 is a linear factor because if we plug in this 1 here, it's going to equal 0. What's great about these numbers down here is they tell us our quadratic factor. Our quadratic factor here is going to be 1x squared minus 11x plus 24. At this point, we can rewrite our function as f of x is equal to x minus 1, our linear factor, times the quantity of x squared minus 11x plus 24, or a quadratic factor. Since this is a quadratic function, we can try to factor it. If factoring doesn't work, we can either complete the square or use the quadratic formula. Our factors of x squared are going to be x, and the factors of 24 both have to be negative because we have a negative 11, and I'm going to use negative 8 and negative 3. Adding up the product of these, we're going to get negative 11x. That being said, we can rewrite our function as f of x is equal to the quantity of x minus 1 times x minus 8 times x minus 3. From this binomial, we know that 1, 0 is an x-intercept. From this binomial, we know that 8, 0 is an x-intercept. And from this binomial, we know that 3, 0 is an x-intercept. Checking these on a graphing calculator, we can see that our zeros are correct. Let's try another one together. Here we have the function x cubed minus 31x minus 30. To find our list of rational zeros, we have to find the ratio of the factors of p to the factors of q. The factors of p are going to be, and the factors of q are going to be. Simplifying this, we're going to have a list of. Coincidentally, it looks like we have 16 possible rational zeros again. Let's start looking for one that actually works. Just like last time, I'm going to start with negative 1 here. For our coefficients, we have 1. There's no x squared, so we have to put a placeholder of a 0 because there's 0x squared. We have negative 31 and negative 30. We're just going to bring this 1 straight down. 1 times negative 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is going to be positive 1. Negative 31 plus 1 is negative 30. And negative 1 times negative 30 is positive 30. And these add up to get 0. And this came out perfectly. Even though we had 16 possible rational zeros, we found one of them on the first try. This negative 1 over here is the x-intercept, which means that the binomial is x plus 1. And these numbers down here represent our quadratic function of 1x squared minus 1x minus 30. From that, we can rewrite our function as f of x is equal to the quantity of x plus 1, that's the 0 we found, multiplied by x squared minus x minus 30. Our factors of x squared are going to be x, and factors of negative 30 have to be 1 positive, 1 negative, and have to add to get to negative 1, so I'm going to choose negative 6 and positive 5. Adding the product of these, we're going to get negative 1x, which is what we want. Rewriting this one final time, we'll have f of x is equal to the binomial x plus 1, multiplied by x minus 6, another linear factor, multiplied by x plus 5, our last linear factor. Here we just factored this quadratic into two linear binomials. If you run into a quadratic that's not factorable, don't forget that you can just use the quadratic formula. From these linear factors, we know the x-intercept, or the zeros, are negative 1, 0, we have 6, 0, and negative 5, 0. Let's check this on a graph real quick. And looking on a graph, this checks out. Let's try a third one together here. The function we have here is f of x is equal to x cubed plus 2x squared minus 15x minus 36. Here we can see that p is negative 36 and q is positive 1. For a list of possible rational zeros, we'll write our ratio of factors of p to factors of q. And for the factors of p, we're going to have... And for the factors of q, we have... Simplifying this, we have a list of... Here you can see that we have 18 possible rational zeros. Now let's try synthetic division to find a rational zero. I'm going to start by trying negative 1. Put that to the left here, and we'll put the coefficients of 1, 2, negative 15, and negative 36. This 1's going to come straight down. 1 times negative 1 is negative 1. Adding these two, we're going to get positive 1. Negative 1 times 1 is negative 1. Adding these two, we get negative 16. Now let's try positive 1. We'll write positive 1 on the side, and write our numbers here, negative 1, 2, negative 15, negative 36. Bring this 1 straight down. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. Negative 15 plus 3 is negative 12. 1 times negative 12 is negative 12. And adding these two, this is also not 0. Now let's try negative 2. This 1's going to come straight down. This will be a negative 2. This is 0. This is 0. This is negative 15. This is 30. And this won't be 0. Now let's try positive 2. And again, this is not 0. Now I'm going to try negative 3. Start by bringing this 1 straight down, and put a negative 3 over here. Add these to get negative 1, multiply to get positive 3, add to get negative 12, multiply to get positive 36, and finally, we get a 0 here. This is good. This negative 3 that worked let us know that we have a linear factor of x plus 3, and these numbers down here tell us that we have a quadratic factor of x squared minus x minus 12. This means we can rewrite our function as f of x is equal to x plus 3, this is the linear factor that we divided it by, multiplied by the quadratic factor of x squared minus x minus 12. Now let's see if we can factor this quadratic. Factors of x squared, we have x, and factors of negative 12, we need one positive, one negative, and they need to be 1 apart to make negative 1x, so I'll choose negative 4 and positive 3. Pairing these up, we will get our negative 1x. Finally, we can write our function as a product of linear factors, so we have here x plus 3, and then we're going to have x minus 4 and x plus 3. The product of these two binomials represents the quadratic above. Simplifying this a bit, we can write this as f of x is equal to x plus 3 squared, since there's two of these binomials, multiplied by x minus 4. From here, we can see one of our x-intercept is going to be negative 3, 0, and we can see here that our x-intercept is going to be positive 4, 0. Looking at a graph here, we can see our two x-intercepts are correct. Now if you're wondering why we don't have three x-intercepts because we have a cubic function, it's because of multiplicity. Keep in mind here that we had a repeat of this x plus 3 factor. At x equals negative 3, our function actually doesn't cross the x-axis. It just touches it and goes on back down. Because we have odd multiplicity for this x minus 4, we can see that the graph clearly crosses the x-axis at positive 4. Let's try a fourth one here. Here we have the function f of x is equal to x cubed minus 3x squared plus 12x minus 36. For a list of possible rational zeros, we'll find the ratio of factors of p to factors of q. And just like the last example, we're going to have the same factors. As expected, we have 18 possible rational zeros. Since this last value is negative 36, we really need to see if we can get this part of the function to equal positive 36. Because we have an odd degree here, if we choose a negative value, we're going to get a negative value to begin with. This will also be negative if we choose a negative value for x. To balance out this negative 36, I'm going to try out some positive values first. I'm going to start with positive 1 here. That didn't work, so I'm going to try positive 2 now. Now I'm going to try positive 3. And positive 3 works. This 3 here lets us know that our linear factor is going to be x minus 3, and our numbers down here let us know that we have our quadratic factor of x squared plus 0x plus 12. This simplifies down just to x squared plus 12. We can write our original function as f of x is equal to x minus 3 multiplied by x squared plus 12. Now let's see if we can factor this x squared plus 12. Because there's no b term, I'm going to go straight into solving by square roots. Setting it equal to 0, I can subtract 12 from both sides here. I can find that x squared is going to equal negative 12. And we can solve for x by taking the square root of both sides. The square root of negative 12 is going to be plus or minus 2I root 3. Since we found out that these zeros here are complex, that means that we can't factor the x squared plus 12. Our completely factored function is f of x is equal to x minus 3 multiplied by x squared plus 12. We found one rational and real zero here of 3, 0. And we found our other two zeros here, which are complex, but we found out they are actually going to be plus or minus 2I root 3. Looking at a graph here, we can see the real zero of 3, 0. This right here is going to be the one real solution. And this right over here is going to tell us our two complex solutions. It makes sense here that we still have 3 total zeros because we had a cubic function. We just happen to have 1 real and 2 complex. Let's try a fifth one here. We have f of x is equal to x to the 4th power minus 2x cubed minus 9x squared plus 10x minus 24. Here's our p and here's our q. Here are the factors of p. And here are the factors of q. All the possibilities just boil down to... Here we have 16 possible rational zeros. Let's get started in finding one of the zeros. Seeing as we have a negative 24 at the end, we're going to have to somehow come up with a positive 24 from these numbers over here. Because of that, I'm going to start with some positive even numbers first. Alright, so that didn't work, so let's try another positive even number. Perfect, this one did work for us. This 4 here tells us we have a linear factor of x minus 4. And these numbers on the bottom tell us we have a cubic factor of 1x cubed plus 2x squared minus 1x plus 6. So far, we can rewrite our function as f of x is equal to x minus 4 times x cubed plus 2x squared minus x plus 6. Now we have to see if we can break this down. Using synthetic division again, let's try to break down this cubic part into a linear and quadratic. We can write down our coefficients of 1, 2, negative 1, and 6. No matter what number I choose, we know that this is going to be positive and this is going to be positive, since squaring any number will be a positive value. That means we need to get this to be negative and this to be negative. The term that has more control in making a larger negative number is going to be this x cubed over here. If I choose a negative number, this will be positive, this will be positive, and this will be positive. This will be the only one that will be negative. I could start with negative 1, but I'm going to start with negative 3 because I think that'll get us a larger negative faster. Let's put that negative 3 down here for synthetic division. And that worked out really nicely here. We now know that this negative 3 means we have a linear factor of x plus 3. And these numbers down here tell us we have a quadratic factor of 1x squared minus x plus 2. This means we can rewrite our function as f of x is equal to the x minus 4 we found out earlier. Now we have this x plus 3 we just found out. And we still have a quadratic factor of x squared minus x plus 2. Now we have to see if we can do anything with this quadratic piece. First, we're going to see if we can factor. We have factors of x squared, which is x and x, and for 2, we need a negative and a negative. So negative 2 and negative 1 are our only options here, and unfortunately that only makes negative 3, so this is not factorable. At this point, you could complete the square or use the quadratic formula, but since our b term is an odd number, I'd rather use the quadratic formula here. Remember, the quadratic formula is simplifying the radical a bit. This is going to be 1 plus or minus 1 minus 8, I believe, so that's going to be negative 7, and that's all over 2. Simplifying just a bit more, we can say that this is going to be 1 plus or minus I root 7 over 2. So here's our final factored function. We have f of x is equal to x minus 4 times x plus 3 times x squared minus x plus 2. It turns out this last part was not factorable. Here we have one real 0 of 4, 0. Here we have another real 0 of negative 3, 0. And here we have two complex solutions, or two complex zeros, and we have 1 plus or minus I root 7 over 2. So we have two real and rational zeros and two complex zeros for a total of 4 zeros since we have a quartic function. And here we can see on our graph our two real zeros. Now let's try a sixth and final example here. We have f of x is equal to 3x cubed plus 19x squared plus 4x minus 12. Our factors of p are going to be, and our factors of q are, we'll start with finding the ratio of all of the p-values to positive and negative 1. 1 over 1 is just 1, 2 over 1 is just 2, 3 over 1 is just 3, 4 over 1 is 4, 6 over 1 is 6, and 12 over 1 is 12. Now for all the factors of p to 3. 1 over 3 is just going to be 1/3, 2 over 3 is going to be 2/3, 3 over 3 is going to be 1, which we already have on our list, 4 over 3 is going to be 4/3, 6 over 3 is just 2, which we already have on our list, and 12 over 3 is just 4, which we already have on our list. We have 18 possible rational zeros. Now we have to look for some zeros. Since we have a cubic function, we just have to find one rational zero, hopefully one from this list here, that can turn our function into a linear and quadratic. Since we have a negative 12 at the end, we need to somehow see if we can get a positive 12 using these values over here. If we choose a negative number, this will be negative, this will be negative, and this will be negative. I know a negative value could work because this value is going to be pretty positive. Let's write our coefficients down. I'm going to start with trying negative 1. And lucky for us, this worked on the first try. This here means that we have a linear factor of x plus 1. And these three numbers down here tell us our quadratic factor of 3x squared plus 16x minus 12. We can rewrite our original function as f of x is equal to x plus 1 multiplied by 3x squared plus 16x minus 12. Now let's try to factor this quadratic. For factors of 3x squared, we can write 3x and x. And for negative 12, maybe I'll try something like 2 and 6 here. These pairs are going to make 6 and 6, which is 12. That's no good. This is going to make 18 and 2. That could work. 18 and 2, 18 minus 2 is 16. So I'm going to throw this negative on the 2 here, since we need to get a negative 12. 3 times 6 is 18, 18, and then minus this negative, or minus this 2x rather, is positive 16x. So I'm going to call these our outers, and I'm going to call these our inners. I'm going to start by writing my binomials out here. The 3x is going to pair with a positive 6, and the 1x is going to pair with the minus 2. If this method was a little bit confusing, feel free to use the quadratic formula or use a different method you have, but this is just how I factor. Don't forget about this x plus 1 we had over here, and that is what our function is. Here we found out that our 0 is going to be negative 1, 0. Over here, if we set this equal to 0, we'll find out that that's equal to, I believe, 2/3, 0. And our third 0 here is negative 6, 0. Notice how all three of these zeros are rational. Even though we only found out one of them here, which was negative 1, our other two are 2/3 and negative 6. And since they're rational, that has to be on our list here, and we do have the negative 6, and we do have the 2/3. The negative 1, negative 6, and positive 2/3 would be the only three that would work on this list of 18 possible rational zeros. Throwing this into a graphing calculator, we can see that we have our -6, -1, and +2/3. I hope these 6 examples helped you practice using synthetic division to find out the zeros of cubic and quartic functions. Keep up the good work, and I'll see you in the next one.